How we doing? Is that about what you got? Cool. All right, now let's talk about the second derivative. So, first of all, the notation's a little intimidating. This is the second derivative notation. You may say y doubled that way if you prefer, but Leibniz notation, why the twos are where they are, that's a little story for a different day. Yes? There should be a 2 where? Here? Oh, okay, gotcha. Okay, so if I go to take the second derivative of that, then that means I need to take what I just found, the derivative first time over, and take the derivative with respect to x of that. And it's just like all math. Whatever you do to one side, you have to do to the other. So what I wrote there in red is my intention, or saying, hey, person reading this, I'm about to take the derivative of both sides again with respect to x. And the left side, when you take the derivative of the derivative, that's the derivative twice over with respect to x both times. Again, stick with me on the notation. We'll get a little funkier when you get to calc 3 when you got multivariable, but if you prefer to write y double, you can. On the right-hand side, though, you can see you need a quotient, and that's pretty common. So you're going to have to do a quotient rule on implicit derivatives fairly often. So it goes something like this. It's usually done in 2 steps. 1 step through and then 1 step substitution. So by quotient rule, do you remember the quotient rule, mnemonic? That's lovely. Okay, so low is the bottom function unchanged. And when we say d high, we're saying the derivative of the numerator function. What is the derivative with respect to x of negative 2x? Negative 2. Minus high, that's negative 2x. Please be careful with your parentheses. Now here's where we need to be on our game. When we say d low, that means we need to take the derivative of the lower function with respect to x. So what is the derivative of the lower function with respect to x? 6y dy dx. Perfect. Okay, and then over the square of what's below is cool. Now, all that's great, but we don't typically leave this here. Can't leave this. So we need to put something in its place that's x and y-ish. So what do we put in its place? dy dx. All right, so your last step then is to take that derivative and replace dy dx with what we found, negative 2x over 3y squared minus 4. Now, if cleanup were required, then you would have some gross cleanup to do, but we're going to leave that there. You follow me? Okay, so to see if you are with me, would you go to your, I'm going to come back to the notes, we'll do those in a sec, but would you go to box 4 in your homework, 42, and try box 4 on set 42. I think I had 2 of those on set 42 that you should now be able to do. First one we'll try, and maybe we'll have some mistakes, but the next one we're going to master it. 6. Valerie, are you here? Okay. Sorry, let me catch up to you and verify you're good. So, product rule. Did you get something like dy dx is negative y over x plus 2y? Okay, cool. So when you took the second derivative on that, by quotient rule, low d high negative dy dx minus high below 1 plus 2 dy dx. Did you get 2 dy dx's you had to sub for? Yes? Oui, oui? Okay. Actually, I'm going to just call that, so if I have the negative, or the opposite of dy dx, I'm just going to call it y over x plus 2y, unless you have a problem with that. Y, 1 plus 2, and in place of that, I'm going to go negative y over x plus 2. Alright, I keep doing my things. Alright, are you with me? How'd that go? Success? Okay, would you try 21 then? Okay. That's gross. All right. Let me know if you disagree or if I made an error that you see or you're not sure where I'm coming from. Takes a while to check your answer on that. It's a lot of looking up and down. Are we good? Okay. Now, the book gives you lots of straightforward quotient rule practice. Bless you. But the AP tends to ask you, bless you, to do quotient rule besides analytically, which is what the book gives you. Take the second derivative, the quotient rule on this equation. AP will actually ask you to do this numerically and graphically. So let's practice AP style material, shall we? I think I'm back on the quotient rule notes on the back side of the quotient rule, maybe? Are we good? Okay. All right. So I give you a table of function and derivative values for two different functions, f and g. If I said evaluate the derivative of f over g at x equals 4, then isn't that something like chain rule? The derivative of f, how will I denote this? Let's say I'm going to take the derivative with respect to x of f over g at 4. All right, so here we go. As always, first get your basics down, what you're going to do, then put in the table values. Do not just start putting in table values. So my quotient rule, low, is g of x. D high is f prime at 4 minus high, oops, f at x. I should be using either x or at. I'm going to use x's and then give an evaluation bar. Sorry, low d high minus high, f d low g prime over g of x squared. All right, and then I will mark my intention to say, hey, I'm about to throw 4 in here. Then I'm going to go to calculator, or table rather. G at 4 is 5. F prime at 4 is minus F at 4. G prime at 4 over the square of what? 5. Okay, so I'm getting negative 5 plus 2 over 25. So my answer is negative 13 25ths. Do you agree? Okay. Try one on your own then. Using that same table, find h prime at 4. So this obviously will pull from the table and chain rule derivative. So obviously, I don't know what that is. Oh. That's gross, am I right? All right. Ready to throw your answer out? 2/3 plus 9? Oh, goodness. All right. So first thing I want you to check is your derivative of the root. Wouldn't you agree that's 1/2 comes down, 2x plus 1 to the negative 1/2, but then chain rule times the derivative of the inside 2x plus 1. You have to pick up another 2 there. So is your root derivative correct, yay? I hope. Okay, and then let's plug and chug. So what is f at 4? 2. What'd you get for the d high? 1 over, you said 1 over 3? I agree. And then root, 3. And f prime is negative 3 over 4. So you have something like 2/3 plus 9 over 4. So if Gosh, oh, now whatever, do it. What do we got? Let's just multiply top and bottom by 3, shall we, to clear the fractions? What do you think? So we get something like 2 plus 27 over 12, or 29 twelfths. All right, can we all follow on that one? Okay, let's do a graphical type quotient rule. So, the derivative of f over g at x equals 3, I would say that this way. Hey, I'm going to take the derivative of f over g at 3. So, by quotient rule, before I start pulling from the graph, I'm going to get my derivative intent ironed out. Low, g, d high, f prime, as high, f, below, g prime, over the square of what's below g squared. All right, so here we go. What is g at 3? G is the red graph. What's g at 3? 3. F prime at 3. How do I get the derivative from a graph? Slope. So what's the derivative of the blue line at 3? Negative 1/3. Minus high. What's f at 3? Blue at 3 is 1. Below, g prime at 3. The slope of the g graph at 3 is 1. And over g at g squared, what is g at 3 again? 3 squared. So I get maybe negative 1 minus 1 over 9. So negative 2/9. What do you think? Cool. You try one, please. So that's about 1.7. What's g prime at 1.7? Negative 1/3-ish? No, 1-ish, right? 1. Right? What's g at e minus 1? Right, e minus 1. Don't you agree that at that point, g is basically just y equals x? So if you put in e minus 1, you get out e minus 1. You follow? Over 1 over e minus 1 plus 1 is e all over the log of e minus 1 plus 1, or log of e quantity squared. What's log of e? 1. 1 minus 1 Let's do this here. So here we go. 1 minus, what do I get when I distribute this in? 1 minus 1 over e all over 1. So I get what? 1 over e. That was a humdinger. Are you with me? Okay then. Is that all on second derivative notes?
Yeah.
Cool. Let's pick up where we left off on set 43. Gosh, this was a bad one to stop in the middle of, but it's out of block things. It's just hard to get through all of it. Comes without. So, do you want a little refresher of what we did Friday? The Riemann sums and summation notation? You're getting one, darn it. I don't care if you want one or not, I'm giving you one. Okay? So if I said, don't worry, just pay attention, don't worry about writing this down. If I said, hey, write a function a sub n for the area under f of x equals x squared plus 3 on 1 to 11 using n right rectangles. Okay, so I hope you remember that the idea is you're trying to estimate the area by the sum of many base times heights rectangles, okay? And the base is delta x, and the height is the function at different x's. We? Okay. Now, if you recall, we also talked about how to find delta x. Delta x is the total region divided into n rectangles. So in this case, delta x, or how much we're going to go by, is 10 over n. Okay? The x sub I, a little more complicated, but remember it went something like this. If you started at 1, because it tells you to start at 1, and you then went over a single delta x, wouldn't this first x be 1 plus a single 10 over n? Yes? And therefore the first height would be the function at 1 plus 10 over n. Then, when you did the second rectangle, you'd go over to x2, and that would be starting at 1 going over 2 10 over n's, and the height then would be the function at that point. Are you with me there? All right, so then we got this counting pattern of it always being 1 plus so many 10 over n's, and the how many 10 over n's was called I. So this x sub I is always the starting value of the region plus I delta x's. In this case then, what's the starting value? 1, and however many delta x's is 10 over n. So I could say that the area is something like 10 over n times the function at 1 plus 10I over n to represent different x's at which you're drawing heights, yay? And this tells you the first I you use. Because I'm using right-hand rectangles, my first value of I would be 1. I start by going 1 delta x over, and my last is however many rectangles I'm using. So in this case, that would just be generally 10 over n. You follow? Do you remember all that? Okay. We then talked about how we could use our calculator to put that into our calculator and talk estimates. Get 5 rectangles, 10 rectangles. Should we review the calculator component or no? You got that? You should review it? Okay. Get out your calculator, please, then. And I will get out my calculator, please, then. Okay? All right. You could start by putting the function in your graphing menu so it's easier to type the summation, and that's fine. If you don't want to, that's fine too, but I'm going to just type in A parentheses N close parentheses, nope, N close parentheses, and then remember the idea of let that equal this function is the colon equal button, which is right above the button next to 9. Let that function be defined as this. Summation is in that same button, but not the second function, not the control, just the normal catalog button. So go next to 9 for the summation, and you should see it somewhere close to the middle, the sigma button. Did everybody get that? Okay. This then amounts to typing it just as you see it. I is 1 is the start, and N is the end. In here, we're going to start by, I'm going to follow Taylor's advice the other day. It's much easier to avoid errors if you use the function or the fraction template. And we're using 10 divided by N for the base. You follow? Now we're going to multiply that by the height. The height goes to what x's are you plugging in and what is the function. So what we're going to plug in place of every x is 1 plus 10I over n, and we're going to do that in this function. So I need to do a blank squared plus 3 kind of general function. So I'm going to use actually 2 parentheses, 1 for the x squared, and then 1 to enclose the 3. All right, so that's going to be my function of blank squared plus 3. You follow? And if I then go back and say, all right, in that I want to put in 1 plus fraction 10I over n, then I should get something like that. Now it needs to be, the whole function needs to be in parentheses, so that 10 over n delta x gets distributed to everything. Okay, so it can't just be one set of parentheses instead. It's got to be 2. You with me? Okay, so if you hit enter, it says, all right, I defined that function as you asked. So now let's check that we are all getting the same results from our function. Let's do one rectangle. One rectangle, I get an estimate of 1,240. You follow? Okay, try one more. Let's go increasing powers of 10. If I said 10 rectangles, I should get less error. So now I'm getting 535, yay? If you try 100 rectangles, you should get a little better estimate. 9,587 over 20, which is about 479.35. Are you getting this? Yeah. Okay, cool. All right. So that's where we were. I also asked that you be able to go backwards, which is to say, if I give you a Riemann sum, you should be able to tell me what the question was. So if I told you this, then you should tell me, oh, that was a person finding area under e to the x on 2 to 6. 2 to 6. With me? Okay. Okay. Now, oh, that's great. The calculator is wonderful, but we could actually get an exact area with a little framework. All right, so evaluate B above for the exact area. I don't have B in front of me right now. Can somebody fix it? Thank you. Oh, hey, I didn't know I gave you this page. Okay, so B above on the back of page 2 is f of x equals x squared x cubed, wasn't it? X cubed on 0 to 3. Okay? Are you with me? Okay, so at the top of page 2 on set 43's notes, we were giving expressions for the area under curves, practicing our summation notation. The question was, what's the area under x cubed on 0 to 3? In question B, we said the area function was from from 1 to n of 3 over n times f of 3I over n. Okay? Okay. Cool. All right. So let's go a little better, and actually I'm going to start writing on the left, like you always should. Sorry, I equals 1, 3 over n. Now isn't the function cubic? Yeah? All right. So really when I say f of 3I over n, it's really 3I over n cubed. Cool? All right. Okay. You with me?
Yes.
All right, so let's go here now. Would you, because it tends to make a little more sense what I'm about to do in the next step, if you have this to look at, would you write this? This is the same as, remember summation notation is just a pattern of functions with numbers plugged in and adding, all right? So this is the same as when I equals 1, I would get 3 over n times 3 times 1 over n all cubed. And then I would plug in I equal 2. And when I equals 2, I'd get a 3 over n times 3 times 2 over n all cubed. You see where I'm coming from? Okay? And then eventually, I would keep doing this. Remember the summation just says start by plugging in 1 into the function, calculate. Then plug 2 into the function for I, calculate. Keep plugging stuff in until you get to the last thing in, which is, this tells you the last I in. Last I in. And that would mean that you end with I of n going in. You follow? So we finally end by plugging in n into 3 over n times 3 blank over n all cubed. You follow? All right. Now, if I wanted to, I could clean this up a heck of a lot. Greatest common factor. They all have this 3 over n. All of them, everyone. And they also have some more common stuff. What else do they have common? The 3 cubed and the n cubed. Now what they don't have common is the 1 cubed, 2 cubed. Those are all different, right? That said, though, can I also take out a 3 over n all cubed? Because that's common to all of them. All of these have a 3 cubed over n cubed. If I do that, if I, from each of those, remove the 3 over n, the 3 over n cubed, all that's left is 1 cubed. And then here, all that's left is 2 cubed and 3 cubed through n cubed. Now, this surely then is 3 to the 4th over n to the 4th, yay? I just cleaned that first because it's compact row. Are you all right there? There's a formula for that. Where is the formula for 3 to the 4th, or not for that? What's the formula for adding a bunch of cubes? Right there. Okay? That's the same as, obviously the sum would depend on how many cubes you added, so it's dependent on n, but it would be n times n plus 1 over 2, all over 2, oops, and all of that whole thing is squared. Okay? All right. Now, this then is a formula for the sum based on any number of rectangles. And you might say, well, didn't I have that before? And the answer is, yeah, I had that up here with summation notation. So why is this one better? Well, let's think about that for a second here. A sub n. Wouldn't you agree that I can, do I want to clean this up a little? Do you want to clean this up or nah, just leave it? Leave it? Okay. So I have 3 to the 4th. Okay, never mind. You said leave it. So why am I cleaning? Okay, I was about to clean it up. All right. So at this point, then you're usually at great. So what? Well, this is where we use the idea of perfect area, which is to say no error, if the number of rectangles goes to infinity. We couldn't take the number of rectangles to infinity here because okay, great, I don't know how to take the limit of that summation notation. I don't know where to go from that. Take the limit on that as n goes to infinity, was it equal? I don't know. But this, if I take the limit as n goes to infinity of 3 to the 4th over n to the 4th times n over n times n plus 1 squared, all squared, and by n behavior, because we're talking infinite. Well, let's start with the powers. What's the greatest n power in the top? N to the 4th, isn't it? N squared squared, so it's n to the 4th, and the greatest n power in the denominator. 4th. So because it's n to the 4th over n to the 4th, we can look at the ratio of the lead coefficients, yeah? That's our n behavior modus operandi. That's how we do it. All right? So the limit then is, well, what's the lead coefficient in the top? 3 to the 4th. If I were to expand it all the way out, which you guys didn't want to do because you're a bunch of sissies, you would have 3 to the 4th, n to the 4th, plus a bunch of other little stuff that I don't really care about, right? And in the denominator, I would have 2 to the n to the 4th or 4 n to the 4th. 4 n to the 4th Therefore, the area is perfectly 81/4. That is 20.25, yay? Are you with me? Look up at the table, please. In B, as you added rectangles, what did the area approach? For B, as we put more and more into our calculator. 20.25. I hope you're approaching something like 20.25. That is no error. That is perfect area. The area. You good? Okay. Now, that said, we don't typically, this stuff, this expansion and all that, I don't typically do that. I will do that in summation notation is way less writing. So let's do this in a little less writing kind of fashion. Is this, so I guess your question now is, should I use the second blue page or that white page I just picked up, which I forgot I just gave you? They're not the same. How much on the white page? Back there. Okay. So, I say you try, but you're not ready yet. So let's do this together, okay? So, what you should be okay on doing is you should be able to get me the delta x, the summation notation step. Can you write the summation notation for this, and then we'll talk to cleaning. In other words, write me the function for A as a function of how many rectangles in. Okay, so can we agree with the delta x of 3 over n? Okay, so therefore when we do our basis times height, the base is 3 over n, that's delta x, f at what? 0 plus, technically, if you want to put that in, great. If you don't want to write that, that's okay. But remember, it's the starting point of the region, which in this case is 0, plus 3i over n. All right, now if I then go a little more detailed, in this case, the function is squaring. So instead of f of, I'm going to say it's really blank squared, and 3i over n is what's going in. Because it's right rectangles, I start with an I of 1 and go to n. Remember, those are not references to the region. It's not 0 to 3. That's not what I represents. I represents how many rectangles or what number rectangle you're on, all right? Are we all good so far? Yes? All right, now here's where we write less. I just said this is pretty much where we're at now. I just said this is the same as if I expanded it, I could take out the 3 over n. I took that out. And I could take out this stuff. In essence, what I was really doing is isolating the I. Okay? So in your notes, right, now isolate the I term. Because the summation notation is just a function of I. The end is just kind of coming along to the right. If I do that, then I can pull out the original 3 over n out front of the summation. And I can also pull out the 3 over n squared stuff in there, which means I can pull out 9 over n squared as well. You follow? And when I do, all that's left in the summation, which really you can think of in parentheses, blank squared plus blank squared plus blank squared, is I squared. All right, anything that's not I-ish, you can just pull out front. Now we're going to go formula. I want to eventually get something I can take an infinite limit on. I want to say, now let the number of rectangles go to infinity. Well, I definitely don't want to let the number of rectangles go to infinity here because I wouldn't know what to do with it. What would I do? I don't know what to do if I take n to infinity. I want to say, oh, this is the same as, or can be found by, this formula. So find the squares formula, which is here. You might ask, do I need to memorize those? And the answer is 100% no. I hate memorizing. That is not worth your brain power. I will give you those if you need them. Do not memorize them. Understood? On the test, it'll just say, you might need one of these formulas, and it'll be there, all right? Now, the formula for squares is m times n plus 1 times 2n plus 1 over 6. You've been doing that in your homework. Remember at the number 25 for the last 5 problem sets, you'd say, hey, verify this formula. Today's why you did that. Okay? Thank you, Saxon. All right, now that is a formula for what? It's easy. It's easy in a complicated algorithm or in a complicated process, which happens in calculus, to kind of lose sight of what the heck you just did. So we just did a whole bunch of stuff. What is it? What does that represent? That finds, oh, sorry. That finds the area under the curve perfectly? Not yet. It finds the area under the curve based on whatever number of rectangles you want. So if I wanted to estimate the area under the curve with one rectangle, I could plug one into that, boom, there's my area, my estimate. If I wanted to use 2 rectangles, I could plug n equals 2 in. That gives me a rectangle estimate of 2. You follow? Now all that's great, but if I wanted to find a 2 rectangle estimate, would I go through all this summation notation, or would I just do it like we've been doing it for 2 weeks? Delta x times f at this plus f at that, done with it, yeah? You wouldn't really do all this mumbo jumbo if you wanted to do 2 rectangles. The whole objective is to now take the number of rectangles to infinity. Now this is very much dependent on your behavior limit skills. Is that the end of this class? Wow, this class was going so fast. You reckon I can get 42 today? I'm not really asking you. Give me 42 today. Thank you. Have a nice day. So lovely to see you. How you guys doing? Good, thank you. Have a lovely day, everybody. I do have tests. If you'd like to see a test in 7th period, fine. We'll go over it tomorrow. Bye. Hey, what's up?
Not much. How are you?
You have a good weekend.
I did. Thanks for not giving us homework. That definitely helps.
It does make it easier to have fun.
Yes.
All right. Maximum class is 88 today. There you go.
Thank you.
Got it, dude. Happy day. Thank you.
Yes, great that. Or you could have heard that she said to download.
I need to go a little faster.
I need to dinner.